Today we go over the exam. All right, first question on the exam was a circuit, combinational circuit. Tell me what it does. And the circuit was as follows. Output of this guy came an OR gate and an exclusive OR gate. That came from A. This came from an AND gate, which came from an inverter, which came from B. This came from C. One of the inputs from the mux came from D. Sorry, one of the inputs to the... You ever have that thing where you can't think of a word? Exclusive OR. Okay, there we go. Do you know that the concept of forgetting a word that it's right on the tip of your tongue is called an aphasia? I have never forgotten the word aphasia. Never been able to call been unable to call that word to mind, which I think is ironic. No, it doesn't help me remember what I was trying to remember. It's just like, oh, I'm having an aphasia. And then I have the same thought every time. I've never forgotten the word aphasia. So as I continue on here, this is an inverter. And this comes from A. I'm redrawing it. In the exam, I had wires going everywhere, but this is just kind of keeping things simple. So that comes from B. And that also goes to this other OR gate, which goes out to FB. And finally, we've got an inverter connected to D. Okay, so that's the circuit that we are trying to deal with. The way I approached this problem was, this is a bunch of smaller circuits. So let me just move this off to the side a little bit here. Whatever I just did was wrong. Take all of that. Move it over there. I need a little bit of space to be able to do this. So I'm going to start my truth table. A, B, C, D. And I'm going to have quite a few things. I probably will run into that B, but 1, 2, 3. You can see that, right? Yes. 4, 5, 6, 7, 8. 1, 2, 3, 4. 5, 6, 7, 8. And let's finish this off. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. I feel like I'm in dance class. 1, 2, 3, 4, 5, 6, 7, 8. Oop. 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. So what we're going to do is we're going to break this down into smaller pieces. So let's start with labeling a few of these intermediate lines. I'll start, let's see, call this T1, T2. I'm looking for ones that are going to be easy to solve. T1 is the easiest. I can solve T2 once I solve for T1. T3 is relatively easy. Once I have T3, I can solve for T4. The output of this OR gate is just FB, so we'll figure that out eventually. So what I'm going to do is I'm going to start looking at T1. Now T1 is just B0 and C. So I'm going to look for every place where B is 0 and every place where C is 1. So B is 0 in the first 4 rows and in the third set of 4 rows. So that's the only place where T1 can be true. The other requirement is that C is also 1. So C is 1 in the bottom half of that grouping of 4. So T1 excuse me, C, did I copy that correctly? CB bar. Yes, I did copy it correctly. Okay. 1, 1, oops, and 1, 1. Those are the only places where B is 0 and C is 1. So 0, 1, 0, 1, 0, 1, 0, 1. That's the only place that is true. Everywhere else, therefore, must be a 0. Questions so far? Pretty straightforward. Okay, now that we've solved for T1, we can create T2. T2 is going to be A ORed with T1. And ORs are really simple because any place either one of these is 1, I know the output T2 is going to be 1. So all I'm going to do is I'm going to look for places where A is 1. That occurs right in the last 8 rows. So automatically, doesn't matter what T1 is in this case, I know that those are 1. Now, in the rest of them, the first 8 rows, A is 0. So in order for T2 to be a 1, or for T1 to be true, we need to look at T1. And any place where T1 is 1, excuse me, any place where T1 is 1, T2 will also be 1. So the remaining rows are zeros in both cases, so that's my row T2. Now, it'd be nice if right now I could calculate FA, but I can't, because in order to know FA, I have to calculate T4. And in order to calculate T4, I need to know T3. So let's deal with T3. T3 is equal to A naught and B. So any place where A is 1, I know I'm going to have a 0. Right? I know it's going to be a 0 because they have to be, both of these things have to be true, both literals. So A bar means A must be equal to 0. So I'm left up here looking for places where B is 1. And that is right there. Everywhere else is also 0 because B is 0 in the first 4 rows. So even though A is 0, B is 0 as well, which means T3 is false. So we're just continuing on. We've done T1, T2, T3. Now that we've done T3, we can do T4. Let's change colors here. T4. So T4 is an exclusive OR. All right, which means we have to exclusive OR things. So in the case of T3 being 1, whatever is on D is going to be inverted because 1 exclusive ORed with X is always X bar. 0 exclusive ORed with X is always X. So we can look at this 2 ways. First off, we can look at all of the zeros, of which there are 12, on T3, and just copy over the column D, because D is the other input. So let's do that. Copy over D, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. Then we look at the second set of 4 here. This is going to invert D. So instead of 0, 1, 0, 1, we have 1, 0, 1, 0. And there's T4. Now that we've dealt with T4, we can find FA. Because FA is just T2 or T4. So any place T2 is 1, we're going to have a 1. So to find that, I'm going to look at T2 first. I'm going to copy over the 1s. Okay. In the remaining positions, I'm going to look at T4. And there is FA. All complete. To find FB, And yeah, just like I thought, I run into it just a little bit. FB is T3 ORed with D bar. So any place D is 0, I know I'm going to have a 1. Any place T3 is 1, I know I'm going to have a 1. So let's start by looking at T3. I know that because T3 is 1 in those 4 positions, that my output FB is going to be a 1. The remainder is just going to be D inverted. 1 0 1 0 1 0 1 0 1 0 1 0. All I did is invert 0 1 0 1, made it 1 0 1 0. That is the complete solution for number 1. It is a little time consuming to write out, but none of the pieces were particularly complicated amongst themselves. Questions on number 1? I have a question. Where the hell are all of you people? Is there another exam today that you're all studying for? You had one this morning, so everybody took that exam and then decided, oh, I'll take a nap. Okay. Let's continue on with number 2. Number 2 is 3 parts, and it involved just drawing symbols. The symbol for a 2 to 4 decoder with active low outputs. 2 to 4 decoder. That's a 2 to 4 decoder with enable. A 2 to 4 decoder with active low outputs. All right, you've known this since chapter 2. A bubble means inverted. Active low is just active low. So instead of a truth table that looks like this, we get a truth table that looks like this. Okay. So that was an active low output. A 4-bit 4 to 1 mux. Let's start by drawing a 4 to 1 mux. There's a 4 to 1 mux. A 4-bit 4 to 1 mux, I even gave you the hint buses. That's it. That's all you had to do to augment a 4 to 1 mux to be a 4-bit 4 to 1 mux. Question? That's not active low. That's active high. Let's just assume that I fail you for the whole exam. I don't know. I haven't finished grading them yet. If someone did, some hypothetical person, a friend of yours perhaps, what would happen? What would the grade be? I would fail you for the entire exam. Like I said, I have not finished grading it yet. Just for that part? That's a fairly major portion of that question. So I would assume a bit. You're not going to get me to give you a number right now. All right. A, B. Part C, a 4-bit full adder. Well, a single bit full adder has a carry in, a carry out, a sum bit, and an A and a B bit. A 4-bit full adder would have 4-bit inputs, 4-bit outputs. It would not have a 4-bit carry out or a 4-bit carry in. It's a single bit carry in. If you put your carry outs at the bottom or your carry ins at the top, I don't care, as long as those pieces are somewhere on that module. In my solution, to be completely accurate, I said closer to A is most significant bit. higher subscript is most significant bit. And I kept that all through my solutions. So when I say A, I mean that is the most significant bit. It's more significant than B. When I give a subscript D3, that is the more significant bit, the most significant bit instead of D0. Okay, so that's how I kept that up. If you had done something, it would have taken you a little bit longer. Something like this. A3, A0, B3, B0. I would have given you that because you still gave it to me. It's just not the easiest way to write it. You could have done it with buses. Other questions on that? Okay. Number 3. Implement the following circuit. F of A, B, C is equal to sigma 0, 1, 2, 5, 7. What did people think of this problem? Thumbs up, thumbs down. Just emphatic thumbs down a few. All right, this was the easier version of the problem I was going to give you. So this says using a 3 to 8 decoder. It was just as easy with this. It was super easy. I was going to make you do it with a 2 to 4 decoder, which would have actually required a little bit of thought. So let's start by knowing what a 3 to 8 decoder is. 1, 2, 3, A, B, C. Easy as my tests are. 1, 2, 3, 4, 5, 6, 7, 8. D0, D7. A 3 to 8 decoder will even provide an enable, although we may or may not use it. Do I do anything nice? Like I connect A, B, and C to the inputs of the decoder, A, B, C to the inputs of the decoder, which means each of these outputs is going to be, because I didn't do active low or anything, that would have been odd, okay? Each of these is going to be active when a particular min-term comes in. So D0 will be active when you see 0, 0, 0, which corresponds to min-term 0. This line will be active when you put in min-term 1, and so on and so forth. So to implement this function, you need the following gate. Zero, 1, 2, 5, 7. Ta-da! No, that would have, well, all right, so this is what I'm going to say. I was going to give you the following problem. You can only use a 2 to 4 decoder. What would you do then? And this is just as simple, well, just a little bit more complicated. So let's look at the truth table that we would have seen for those min-terms. 1, 1, 0, 1, 1, 1. Okay, min-term 0, 1, 2, 5, 7. So all we've got now, though, is A and B hooked up. Like so. So what am I going to have? I'm still going to have a big OR gate here. But what I'm going to do is I'm going to look at each group of 2 and make a little mini circuit out of it. So this first circuit, that's just always 1. So I'm just going to hook it up right there. This next circuit, C bar. The third circuit is C. And the fourth circuit is also C. You could simplify this a little bit. You could combine them up a bit. So you could put like an OR gate there coming out of D2 and D3, D0, D3, and then that could go into that AND gate with C. That would simplify things a little bit, but it's the same number of gates. And that's F. Okay, so that's how I would have done it if it was only a 2 to 4 decoder. But I looked at that and I said, we didn't do that in lab, so I was nice to you. And I continue my thing. A, most significant bit. D3, most significant bit. So to make sure that my A's and B's match up with my D0s and D7s and so forth. All right. Not last question. Next question. Design a 4 to 16 decoder. Actually, do it over here. 4 to 16 decoder. 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Ooh, that was kind of an iffy 16 there. 16. 4 to 16 decoder using 2 to 4 decoders. I do not specify about enables, so you get to choose if you want to use enables. One way is easier than the other. And a minimum number of external gates as needed. The correct answer is 0 external gates. You got to label everything. So the rules that I gave you are take 2 to 4 decoders, and I'm going to draw one really good 2 to 4 decoder here. A, B, D0, D3, 1, 2, 3, 4. Enable, like so. Take one of these, group it together, duplicate it until you have a total number of outputs that matches the requirement. In this case, that total number is 16. So there are my 4 2 to 4 decoders, and I'm going to label those now. This is my output D0, and this is my output D15. X? All right, I will label it X0 and X15. The next step is look at your enables and repeat. So I need 4. So I'm going to take one more of these gates here. Boom. Okay, and hook those up. Question?
No, it's have to be the X0 to X15.
I will draw that one out. I'll show you. There'll be a few things that are different. Okay. So there I've got my enables hooked up one at a time. Oops, went a little high. Low. And across. Okay, hooked up. At the point where I have one enable, I know that I'm done. How do I hook up my select lines now? My select lines are labeled S3 through S0. So we got to have a little bit of a meeting of the minds on what our most significant bit is. My most significant bits are A and D15. Okay, so the larger the subscript, the more significant the bit. The closer to A, the more significant the bit. So this bit here is the high bit of this 2 to 4 decoder, and B is the least significant bit. So when they're both 1, D3 will be active. With that in mind, I'm going to hook up S3 and S2. Over here in parallel, I'm going to hook up S1, 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 S1 to the A inputs, and S0 to the B inputs. That's it. I would probably say that I have an enable input going into this, and that's my device. Now, if you label this the opposite way, 0 at the bottom, 15 at the top, you might be Okay. But here's what would have to change.
You have to flip the S.
You'd have to flip a lot of things. Let's Control C that, go to a new page, paste it. Crash it. Okay. Open board. Let's see if I have that documents. Okay, I can pick up here. Let's try that again. Oh. One more time. Over here, grab all of this, group it, Control C, next page. Does not crash this time. Okay, so if you labeled this a little bit differently, there are a few things that would change. I'm going to make this a little bit bigger so that you can see it. If you labeled it such that such that this was x15 up here and this was x0, we have to deal with a lot more stuff going on. We could say, let's see, how would we do this? We would have to say D0 is most significant bit. I think actually that might be the only change you need to make. If you did it that way, then when you put in a 1, 1, D0 would go out. Or D0 would be active, I should say. We'd see a 1 there and a 0 there. That's not intuitive the way I think about it. I think if you put a 3 in, D3 should be active. But that's one way that you could have made that correct. Another way that you could have done that, let me fix up S1 here. Another way you could have fixed it is by leaving D3 as the most significant bit, but changing the way you labeled things. So you would label this D3 and that D0 on all of them. D3, D0, D3, D0, D3, D0, and you'd also have to do it over here, D3, D0. What you've done in effect is given me exactly the same circuit, right? Because if I put in a 0, 0, with the idea that D3 is the most significant bit, D0 would be activated, which means that guy would be enabled. And then if I put in the other 0, 0 here for the 4 bits, that would act, oh no, yes, oh no, that would still work. It would activate this input, which is connected to X0. Activate that output, which is connected to X0. So, yes, there are multiple ways to answer this question, but I tend to think, top down. So, X0 at the top, X15 at the bottom. How I do it. If you had done, you could have done something weird where it kind of counted X3, X2, X1, X0, X7, X6, X5, X4, sort of backwards here, backwards there, backwards there, backwards there. You could have done something like that, but there's a large chance for mistakes there. Okay, questions on that? Okay, let's move on. Oh, this guy. The drawing that was given to you looked something like this. And then stuff. I'm not going to redraw this stuff. Big matrix, you have to trace it out. What I will do for you now is I will say, all right, this was 4 NAND gates. And if you traced it out, you saw that all of the bottom pins were connected to E bar. So rather than redrawing that mess, let's do a little analysis. E bar. And then we had the other two inputs here. And the first two were connected to A bar and A bar. The last two were connected to A and A. Then it went B bar, B, B bar, B. So effectively what we had was A bar, B bar, A bar, B, A, B bar, and A, B. So effectively 0, 1, 2, and 3. We also had everything connected to E bar. So what kind of a device was this? This was a decoder. It takes a binary number in and gives you a single output high. Now, decoder. The next question, how would you specify the size and type of this device to another engineer in words? In other words, if you wanted to go to a stock room and get a chip that had all these properties, what would you say? Well, first off, we know it's a decoder. Specifically, it's a 2 to 4 decoder. However, there's more to this. A regular decoder, as we saw a few slides ago, somewhere, has that kind of a truth table. That is not what this one has. This one has this kind of truth table. So it has active low. So with active low outputs. Furthermore, it has an active low enable. So if we were drawing this device as a schematic symbol, we would have the following setup. AB enable would be active low, as would all 4 of the outputs. Okay? Questions on that? All right. Well, if that is the end of the exam, quit this. I'd like to go on the internet for a moment and show you a few things to start off chapter 5. Come on. It's got to load up here. Google Chrome. Yes. Let's try doing this. Duplicate screen. And now I got to check back with internal display. Oh. Okay. And maximize. So I want to show you a circuit. Oh, don't be simulating yet. What I've got here is 2 inverters. Can everybody see this reasonably well? Okay, I've got 2 inverters. Now, what are the rules of inverting something twice? It's just the same thing. Over here, I've got a little logic indicator. Red is a logic 1, and blue is a logic 0. Over here, I've got a lamp. It'll light up if it sees a 1. So, I also have a switch here, so I can disconnect it. Now, if I start simulating this, what I see is 0, which is blue. Those little green dots, those indicate current flowing. So 0 comes in, and out of this inverter comes red, a 1. And then it goes to another inverter, and it's low. If I change that, now it's a little lamp. It's like on fire. I think that's cute. I think that's very cute. Like so. Now, the interesting thing about this is if I completely disconnect the switch, That light is still on because this circuit reinforces itself. All right, this first inverter has a 1 on the input, right? Because I connected it via this switch. Has a 1 on the input, which means it outputs a 0, which means this inverter outputs a 1, which is also connected there. So I'm actually physically driving the input of the first gate here. And as I change it, the light turns on and off. Seem reasonable so far? Okay. Once I disconnect it, though, the fact that there's this line in the center is reinforcing that signal. So the output of this first gate provides the input to the second gate, and the output of the second gate also provides input to the first gate. This is the start of computers having memory. 2 inverters, that's all you need. You also need this switch, right? So you set it, and then when you stop providing input, I don't mean you provide a 0 input, you mean no input. It's completely disconnected. I can twiddle this now, and notice there's no change in the light. Can you see kind of that it's showing me when things are transitioning high and low? Okay, good. All right. So that's my first demo to you. 2 inverters are a way to provide memory. Now, I'm going to do something a little crazy here. I'm going to move a few things around. Haven't changed anything. Same circuit. All I did was move it, and it auto-routed these wires for me. All right. I'm going to add in another lamp. So the only thing I've changed is the circuit now has 2 lamps. And if I go back to simulating this, this is an interesting case, and I want to pause it right here. I want to pause it. Something weird is going on right now. The lamps are neither on nor off. They're sort of in this transitional state. Look at what's happening on the output. So right now, it looks like I've got a 0 on the input, blue is 0, and I've got a 0 on the output, which makes no sense. That's weird, right? We should see, whatever the input is, we should see the output. Well, let's follow this through. Right now, we don't know what's going on. If I were to connect this, okay, even just for a second, suddenly everything settles out, and this top lamp is off and this bottom lamp is on. The reason we saw this the first time is because we didn't know what our memory was. Okay, we have to have an initial state for these new types of circuits. Once we do have this, though, it's clear right now what's going on. When I make this a 1, it sets this guy up. When I make him a 0, it sets that guy up. They're opposite of one another, so they will always be opposite. As I turn one on, the other turns off. And you can see what's happening. Now, the only thing I did was I changed the orientation of these inverters. I could always go back, well, sort of go back here. And this is the same circuit that we saw before. It's 2 inverters, and the output of this second inverter reinforces the input of the first inverter. And then let's put it back in place now. Unfortunately, this isn't really useful for us. It is nice that we can disconnect it, and it keeps its memory. But we'd have to manually flick this switch. There aren't a lot of switches inside of semiconductors. That's not a thing that we typically have. But we can build on this. I'm going to take this same basic idea. I'm going to replace these inverters with NOR gates. Yeah, we're getting towards experiment 8. That's right. So let me build this guy. Don't discharge. Or save changes. Load up this example. This, by the way, is a website called everycircuit.com. It's free. It's super fun. There's even like an Android app. You can do this on your Android app. So here you see that same initial problem. I've still got NOR gates. It's still this cross-coupled design. But right now it's kind of like, I don't know what's going on. Now let's go back to open board for just a second. because I want to talk about NOR gates for just a moment. So with a NOR gate, not OR, 1, 0, 0, 0. I'm going to look at this in terms of this being a fixed input and then the other one being a function. So here, if I split this up across, 1 NORed with X is always 0. 0 NORed with X is always X bar. This is just, an extension of the theorems and postulates we already know. All right? Because the postulates we already know, 1 or X is always 1. 0 or X is always X. So if you invert both sides of these equations, you end up with this. All right, so knowing that, okay, let's go back to that every circuit diagram. Oh, look, something has changed. It's actually settled out to something, and that's to be expected. Let's go back. Right now, we're in an unknown state. The only other change I made to this is I actually have 2 logic inputs now. Okay, so what I've got is 2 logic inputs set at 0. Let's look at that. Let's draw it out and see what happens. NOR gate, NOR gate. This, by the way, is the pretty way to draw cross-coupled latches. It looks much better here. And then I have my 2 outputs. Now, if I start if I start everything out at 0 like this, what is 0 NOR 0? I'll bring my truth table over here for a second, hopefully without crashing it. Get rid of that. And this still shows up kind of okay? Yes, it does. So 0 NOR 0 is what? 1. That's right. It's 1. And in fact, both of these are 0 NOR 0, so they're both 1. All right, so that means that 1 is going to propagate over this wire, like that. And this 1 is going to propagate over this wire, which is also 1. Now, we've got a new system that we have to evaluate. What is 0 NOR 1? 0. So that's a 0 and that's a 0. And that means those zeros are now going to propagate over here. 0 and 0. Which, wait a second, we already did this problem, didn't we? Isn't 0 NOR 0 1s? This is going to repeat basically forever, which is exactly what we're seeing here. We're seeing that this sort of brightness is an indicator that it is what we call astable. A meaning not stable. It's just going to keep flickering like a crazy person, okay, forever. Now, if we let this simulation run for long enough, eventually what's going to happen is because of differences basically down at the silicon level, differences in propagation delay, eventually one of these will get ahead of the other. And I'm hoping that I can vamp long enough for that to happen, okay? I don't think it's going to work today. So this is just a simulator tool. Eventually, it'll find itself. If at any point, however, I set one of these high, it instantly snaps into a known state, which is awesome. So what I've got here now is a system that is stable in all cases. All right. And what I'm going to try and do is look at this system in terms of a couple of inputs. So first off, I've got to name these guys. Excuse me, put these both at 0 here. Putting that high, putting that high. All right, so the way I have this set up, I'm going to call this top guy R. Okay. R. I'm going to call this bottom guy S. All right. Did I do that right? Yes. And I'm going to call this guy up here Q, and I'm going to call him Q bar. Now, question. One step. Let's walk through it. I think you might be thinking of the NAND gate. Let's step through it. So, because I have some knowledge already, in state 0, 0, where they're both 0, okay, it looks like right now I can twiddle this bit and it doesn't affect the output. It still always leaves this guy on, okay? And that's okay, because you're going to see that this 0, 0 state is actually a hold state. It's going to just not affect things. Let's do something that makes it change. So here I am now, this hold state, going back and forth between 0 and 1 here, the output is not affected. So when let's actually go back to that unknown state. Here we are in an unknown state. If I turn this guy on with a 1, that causes this LED at the top to output. The reason this works, S stands for set, R stands for reset. Okay? You're thinking of NAND gates. We'll get there. So when I put a 1 on the set pin, what does that do? That puts a 1 here, and we know that 1 NORed with anything is a 0. It doesn't matter what this input over here is. Doesn't matter. As a result, this 0 propagates over here, and let's clean this up a little bit. We need a little less stuff. Going on here. Okay. So if all we know for the moment is that, erase that down there as well. Erase that. If all we know, darn it, let's try that one more time, is that this is a 1 and that is a 0. It doesn't matter what's here. We know that the output here is going to be 0. We still can't evaluate this because 0 NORed with something is going to be this thing inverted. So this has to propagate across. Now we have 0, 0. So what's the output of 0 NOR 0? 1. And that 1 does propagate over, but it doesn't affect anything because 1 NORed with anything is always going to be 0. So we have a stable configuration here with 1 on the output Q, and 0 is Q bar, which makes sense. We've inverted it. That's fine. That's great. If I do it the opposite way, okay, if I put a 0 here and a 1 here, the same process applies. 1 NORed with anything is always going to be 0. That 0 propagates over here. 0 NORed with 0 is 1. That 1 does propagate, but again, doesn't matter. This is a stable configuration. So when you put a 1 on reset, you get a 0 on Q. When you put a 1 on set, you get a 1 on Q. So reset causes Q to go low. Set causes Q to go high. Some interesting things, however, can occur. If I set them both on, that causes a problem because now they're both 0. Now this is a stable configuration. You'll notice that it's not bright white here. It's a stable configuration. They're both off, which sort of doesn't make sense because we kind of want Q and Q bar to always be opposite of one another. What I'm going to do is I'm going to pause this simulation. I'm going to see if I can make this work. It might not. I'm going to set them both to 0 at the same time. Now I'm back to an astable configuration. For a second, it did eventually, yeah, good, excellent. I'm glad that did occur. It does eventually figure itself out because there's a certain propagation delay in these, and it's not going to be exactly matched. So eventually, 1 will take over. So what did it take over as? It took over as a Q. And the 0, 0 is what we call a hold state. When they're both 0, we're holding. I encourage you to play around with this. It's very user-friendly to put this together. But all I've really done is put 2 inverters together so that the output of this first guy influences the input of the second, and that it does this. this idea here is called cross-coupled gates. The output of one goes to the input of the other in both cases. So we're going to, on Monday, continue with this. We're going to look at building NAND gate versions of this, okay? And we're going to formally define how this works. But I wanted to show you this as something you can play with, and as you click these things, again, now I've got my invalid state. To show the astable configuration, I do have to pause the whole simulation, toggle both of them, and then restart the simulation. Now, it might, it did. It actually stabilized to a different state, which I find fascinating, okay? So that's something interesting to play around with over the weekend, because that's all you guys do on the weekend is think about my course, right? All right, look for your exams on Monday. Do tell your friends about this, because we're going to continue to use this. And now I've got to stop the